In this video, we'll look at metallic bonds. I really do think the best way of describing a metallic bond, so a bond between metal atoms, is kind of what they've got up here. A metallic bond is the electrostatic attraction, which electrostatic just means attraction of oppositely charged particles. So it's this attraction between the free moving valence electrons and the positively charged metal cations. Metallic bonding is modeled as a sea of electrons. I really like that. We use this term sea of electrons a lot to describe metallic bonding. And it is just that. So here's this model of gold, and you're going to have your positive nuclei. And so the little orange dots are the positive nuclei. And then the darker blue represents the core electrons. Okay, so we've got the nucleus, we've got the core electrons. But the valence electrons are kind of free to move and flow amongst all the other nuclei. So the valence electrons are kind of in this area that would be the lighter blue color around the darker blue and the orange. So on the inside, I've got my nucleus, and then the darker color would be my core electrons, and so the core electrons are not going to move. It's the valence electrons that can move, and so you've got like this area where there's negative electrons, and it is kind of thought of as a sea of electrons where they're transferred amongst all the positive nuclei. And so it's hard to say like where the electrons are exactly going, which is a little different than like traditional ionic bonding. For example, like in question 10, when we think about the bonding between sodium and chlorine, we know that in sodium chloride, one electron is transferred from sodium to chlorine. Sodium's got one valence electron. It gives away that one, and we know exactly where it's going. It's going to the chlorine. And it's a little bit different here that in a metal, we know that the metals all form positive ions, so they're all going to lose electrons, but they don't have a distinct destination. They're just kind of transferred amongst all of the positive nuclei. So in the middle, maybe I could put like, these nuclei are all positive, and the electrons are like a sea where they kind of move and flow amongst all the positive nuclei. So in question 10, explain how the bonding in sodium is a little different than sodium chloride. Maybe we could say that in sodium metal, the electrons are transferred among many atoms. So there's just no distinct destination. I know this gold atom is going to give away some electrons, but it's not like they're going to the chlorine. They're just kind of free to move amongst all the positive nuclei. So sea of electrons, just meaning that there's all these free moving electrons amongst the positive metal nuclei. And that does then affect the properties that, we say metals are malleable, that we can pound them into a thin sheet. They're ductile. We can draw them into a thin wire. And it's because of the sea of electrons that we don't have rigid bonds here. Because the electrons are free to move, the nuclei are kind of free to move. I mean, think about a bunch of like positive nuclei that are just kind of in a jello sea of electrons, where it's not like a rigid structure where I can move the positive nuclei through some jello, if like the jello is kind of like the sea of electrons, and then that would mean that I could change the shape. I mean, if I like punch a thing of jello, I can change its shape. And that's kind of what happens here with the metal nuclei, that if you start to pound the nuclei, they can change shape. Like maybe in here was where the hammer hit. And because it's not a rigid structure, the sea of electrons can just move and allow the nuclei to move as a result of a change or an impact, like a hammer. Question 11, when copper wire is made, a copper rod is pulled into a narrower wire. Explain how metallic bonding allows this to happen. It's the sea of electrons, that there's no rigid structure. Because the electrons are free to move and flow amongst the positive nuclei, that also allows the nuclei to kind of move and flow amongst the sea of electrons. Other properties that we kind of look at are maybe melting point, that metals in general have really high melting and I guess kind of boiling points, although rarely do we boil a metal, right? I mean, boiling is the change from liquid to gas. I mean, you can have some gaseous metals, but often we think about melting them, and it to some extent depends then on how many electrons are being put into the sea of electrons. And so they give us this example of sodium. Sodium has a relatively low melting point, that you could put a little piece of sodium like in a metal spoon, and you could heat it in a Bunsen burner, and I could melt sodium in the lab in a fume hood, and it would be relatively safe. Sodium melts at 98 degrees Celsius. Magnesium, on the other hand, has a pretty high melting point, 649 degrees Celsius. And so to some extent that depends on the charges, and we think about Coulomb's law and the magnitude of charge that affects the strength of the attractive forces. So in sodium, I only have one valence electron to provide, and so then I'm left with a positively charged sodium ion and just one electron provided to the sea of electrons. Okay, well then if I compare that to magnesium, the magnesium has two valence electrons to provide to the sea of electrons, and it forms then a +2 ion. So because the ion charge is going to be higher and there's more negative electrons pulled into the sea of electrons, that's going to leave magnesium with a higher melting point. And I guess boiling point too, even though again we don't usually think about boiling metals. But it's a lot of Coulomb's law. That guy just never dies, right? Coulomb's law is here forever. That as we have higher charges and more electrons provided to the sea, it just creates stronger attractive forces. And that results then in the lab in a higher melting point. Some examples of that might be like in number 12, that obviously when we make pots and pans, we wouldn't use sodium for many reasons. Number one, sodium reacts with water, which is kind of crazy, but I guess that would not be a safe metal to use in cookware. But also it has a really low melting point. And so, yeah, I wouldn't want to be heating a metal that could potentially melt when I have it on the stove or in the oven. And so often cookware is made of copper, aluminum, iron. Well, for sure aluminum tends to form a +3 ion. So aluminum would be +3 ions, and they would donate 3 electrons. So we're going to have pretty strong charges. I mean, really, like a +3 is a pretty high charge for a metal, especially like the common metals outside of the transition group. So yeah, we're going to have high charges, and that's going to create strong attractive forces, and then that should result in a high melting point. When I think about copper and iron commonly form, like copper is often a +2 charge, donating 2 electrons. Iron is commonly either 2 or 3. Let's say often it's iron plus 2, or iron plus 3 is pretty common as well. So donating 2 electrons or 3 electrons. But when I also start thinking about elements in the transition metal group, they just have lots of protons in the nucleus, which then means that there's a lot of electrons in the energy levels. And so you've got these positive nuclei that in copper, and there's 29 electrons, or I should say 29 protons in the nucleus. 29 protons. And even iron is 26 protons, regardless of the charge. So we end up with pretty positively charged nuclei, which will then create a pretty strong attractive force to the electrons. Now, obviously, there are transition metals that have even more protons than 29 or 26. And we also, for cookware, have to think about elements that are relatively stable and I guess like realistic to use. That, yeah, I mean, something like gold and platinum have really insanely high melting points, but they're hard to find, and in nature you would have to like mine them and purify an ore. They're just really expensive and very rare, and so it wouldn't be feasible to use like platinum to make common cookware. Now obviously we make jewelry out of platinum and obviously gold and silver because they have such high melting points and they're very durable metals, but it wouldn't be something that I would widely use in cookware. And so that's maybe why these are 3 good choices, that they form ions with relatively high charges, and especially then with the copper and iron, they're readily available. We can find them in ore, and it's cheap to then refine the ore to get the pure metal, and they would have pretty positively charged nuclei, which would create strong attractive forces and high melting points. And so then finally, question 13 talks about gold and gold leaf, which if you've taken art and metals, I think they have some of this downstairs, that it's like super crazy thin, like it's even more thin than tissue paper, like crazy thin pieces of gold. And the question here is just kind of asking, like, how does the bonding in gold make it possible to make gold leaf, which is just insanely thin, like I mean fractions of tissue paper even. Well, it just goes back to the sea of electrons, right? I'm going to say that again, the sea of electrons, in that there's not a rigid structure. It's not that the electrons are going from one gold atom to another, and that creates a very rigid crystalline structure where you have these ions then that organize in a pattern, oppositely charged ions, very rigid crystal structure, like an ionic. Here, the electrons are just kind of sent out to flow amongst all the positive nuclei. And then that allows me to pound it really thin, because those atoms can just kind of go into a really thin layer, because the sea of electrons allows the positive nuclei to move.